studying research radioactive waste. And so you have to consider what's in it. And so the amount of the radionuclide, we have actually legal limits from our Environmental Protection Agency. So that's, they say, okay, you can't, you probably have the same kinds, I'm sure you have, limits. In Italy, the government says you may have no more than 1 part per billion lead in your drinking water. That's this kind of thing. And quite often it's not related to anything technical. There are many limits, and when you try to find out where did the limit come from, oh, it's the lowest number we could measure. So in 10 years the limit goes down. I'm completely serious. I'm not joking about that. There are many cases like that because obviously if you have a limit, you have to be able to measure it. And 50 years ago, the limits for lead would be much higher because you did not have the ability to measure, for example, 1 part per billion. It was 50 parts per billion or less. And so that's really an important thing. Another is the solubility and how they interact with minerals. And so if a particular radionuclide is very insoluble, you don't have to worry about it so much as if it's as soluble as sodium chloride. This is one of the most important things, the physical and chemical forms. Several of the radionuclides in the waste are present as gases. Now you have a problem because you have to treat it completely differently. A number of the worst are present as very complex ions. And so they don't interact with minerals the way we expect. And unfortunately, a couple are present as anions. If you think about your mineralogy, and for example, a feldspar, why is potassium in the feldspar? The potassium is in the feldspar to balance the charge that comes from substituting aluminum for silicon. So most minerals are cation exchangers. They're not anion exchangers. So if you have an anion, it comes by a zeolite or a clay, and they don't even see each other. There's no interaction. So that's very, very important. And lastly, half-lives. And so if we put all these together, that tells us what are the important things and what experiments do we need to look at. And this is the list. So look at number 1, carbon-14. It's a gas. There's not a lot of it, but what is in there is going to be quite mobile. So how can you get rid of carbon-14? Precipitate as calcite. That's a good way. Good idea. Neptunium, plutonium, americium, those are very, very bad because they exist in these very large complexes. Look at this. This is one of the neptunium complexes, NPO2CO3 minus 1. So not only is it huge, and so what charge it does have is very diffuse, but it's negative. And so neptunium does not interact very much with much of anything. Plutonium and americium are worse. And in fact, we don't even know all the speciation of these. If you think about speciation, you think when you dissolve magnesium chloride in water, you get Mg+2 and Cl-. And then you have some other magnesium species, but nothing like this. So these are really nasty. Anionic species, the technetium and iodide are always anionic, and technetium is large. So very big problem. Technetium, by the way, is very commonly used in medical radiation experiments. And so most of your medical waste will contain technetium and its daughters. And the interesting thing is there's no strontium-90 and cesium-137 on this list. And the thinking is that these have half-lives of 30 years, and the idea is that any engineer can build a container that will hold this waste for 300 years. Maybe not more, but okay, come on. We can at least hold it for 300 years. By that time, 10 half-lives, most of these will be gone. There's a little bit of cesium-135 that has a 2.2 million year half-life, I think. And so the two original bad actors that we worried about, now we don't even worry about. You put this material in a stainless steel container, and in 300 years, there's none left. It's gone to the daughters. these are important though because they're the two things that produce the heat. So we did a lot of early experiments on radionuclide retardation and sorption using whole rocks. We actually took Yucca Mountain rocks. And it was kind of interesting. We got sorption ratios, remember those RD, and they found, believe it or not, when the project first started, the chemists were working in their place, and we were working in our place, and we didn't talk to each other so much. And so they said, ooh, these rocks have very high sorption ratios for cesium, strontium, and barium. And we analyzed the rocks by X-ray diffraction and said, oh, it correlates with the presence of clinopyroline. And the sorption ratios were up to 10 to the 5th. Huge. If you put cesium in a batch experiment, so you grind up some rock, put it in a beaker with some solution containing cesium, almost all of the cesium went into the rock. And it went into the clinopyroline. And so the early experiments, these were literally around 1980, said, ooh, these are great for all of these. But then, of course, we learned that cesium and strontium aren't particularly interesting. So much for that. So we began focusing the sorption experiments on lanthanides, the neptunium, actually on actinides, I should say. Neptunium and plutonium and americium are actinides. And they did a lot of experiments on lanthanides because you can do similar experiments on non-radioactive material. And so look at these sorption ratios. Plutonium was around 100, but you can do an experiment one day and you measure 100, and the next day on almost the same sample you measure 1. Neptunium is the same way, but always very low. Technetium less than 1, and in fact it implies if you have, there are some cases where you have these anionic species that the water might move, well, this is not a good example because water doesn't move this fast, 1 meter per second, and the technetium moves 1.1 meter per second. It moves faster than the water due to something called anion exclusion. Essentially it's being pushed along and it goes faster. And so it's a real process, and so technetium really is a big problem. So the reason for the variability lay in the fact that we have trace phases, something like manganese oxides, and we started learning about those. And fortunately, we found that some of these very low values can actually still be useful. This is an example of what was then a very complex simulation. It was done using finite element methods on large computers, and we instantaneously injected a non-sorbing and a sorbing material, and we had a flow of, infiltration of 1 millimeter per year, and we mapped the movement of the non-sorbing, basically this maps the movement of the water, and the sorbing when we had an RD of 2.5, so not much sorption at all. But in fact, we had an effective retardation of 8, meaning the sorbing tracer, which was neptunium, even with a very small retardation, or rather RD, moved 8 times slower than the water. So even a very small interaction with the solid material slowed the movement of the radionuclide tremendously. So we learned that a small amount of sorption can do a very large amount of retardation. So you can imagine if we had 10 to the 5th, this pulse would be right where it started. It wouldn't have moved if the KD were 10 to the 5th, or RD. So another thing that is probably one of the most satisfying parts for me was using geochemistry to learn about past transport. In other words, we make these predictions. Are they real? Did it really happen, or could it really happen this way? And so that tells us what really happened, not all of these things that we have in the textbook. And the really nice thing is we can learn something about matrix versus fracture flow. So we can start to learn about these transport pathways. And we used naturally occurring elements as proxies, or I wrote the Italian just in case you you weren't familiar with the use of this term, but instead of we don't have a natural source of plutonium in the rocks. We actually have a fair amount of cerium in the rocks. It's naturally occurring. We also, of course, have a fair amount of strontium in the rocks naturally. And we were able to use those. That's, of course, a good proxy for strontium and cesium. So here's an example for strontium. And this is the distribution. You can see we're just a small piece from 320 meters down. Large amount of clinotillite with lesser mortonite up to about 80%. And groundwater has been infiltrating Yucca Mountain for the past 12 million years. And we have some evidence for the composition of the groundwater from deposits. But you can see that strontium coming through this, what is a welded devitrified tuff, hits the top of this zeolite and almost stops. It's smeared out, and if you wait another 50 million years, that pulse will move down, but you can see there's a very important, significant concentration of strontium at the top of the zeolitic horizon. That tells us that these rocks have really acted as retardation barriers for the simple radionuclides, simple cationic radionuclides like that. This actually is native to this particular bedded tuff. It's inside the feldspar. Here is another example. Again, here's strontium in this dashed line. This solid line is the concentration of zeolite. This is the bedded tuff, and we can see zeolites here. And over here on the right is cerium. And right at the top of this, and at the top of this, in these two units, are fractures that are lying with a very thin coating of manganese oxides. And we did a lot of studies to try to understand what they are. We had to use the scanning electron microscope because they're very, very thin. And we found a couple of different manganese oxides. Manganese oxides are important because naturally occurring manganese oxides are primarily +3 and +4 manganese. And manganese is very easy to be reduced. So if you have a manganese +4, it can be very easily, if you have cerium +3 coming, and it sees the manganese +4, manganese says, okay, please, let's share electrons. And so cerium goes to +4, manganese goes to +3. Cerium +4 is insoluble. And it is adsorbed to the surface of the manganese oxide. And we see this in nature. So we know that the fracture minerals have acted to stop things like, in this case, cerium, but also we assume, and we've actually done experiments to show that it works just as well for neptunium and plutonium. And when we analyzed some of these manganese oxides by the scanning electron microscope, some of them had up to 3% cerium. Tremendous amount of a fairly unusual element. So it really worked. So the natural system really works the way we projected that it would work. Now, I've done a lot of work on one of the other things, thermal effects. Most thermal effects are bad. They do bad things. There's not a lot of good things that come out of this. And they include, as I mentioned earlier, the dehydration reactions, because the zeolites in the clays are hydrates. They contain H2O molecules. And so when you heat them, they produce H2O vapor, and if it condenses liquid. When they dehydrate, they contract, giving you cracks and new pathways between the cracks. We can potentially have dissolution and precipitation, and we've seen evidence of that. That's going to change the permeability, and if you do it for longer term, you actually can potentially eliminate some of these things like clinotillite. So lots of geochemical, digenetic kinds of things going on. And so we did some pretty interesting experiments. This is an example just to tell you about the magnitude of the thermal effect. Whenever you place spent fuel in the repository, again, this is exaggerated vertically. This is an example of a model where we had 114 kilowatts per acre of spent fuel, 30 years old, so it's already gone one half-life for the cesium and strontium. This is 2,000 years after replacement. And at 2,000 years, there's a dry out zone where that volume of rock within here is above 100 Celsius. That's important because the liquid water moves out as vapor. There's water in the pores, and the water moves out as vapor, and at the top, when it's below 100, you have some condensation here, and then you have drainage, and you have condensation here. So there's a large volume of rock that sees temperatures above 100 Celsius. There's nothing magic about 100 Celsius, but this is dry, very large dry out zone. And so that's going to happen in any time you have spent fuel. The kinds of waste that you have in Italy, for most of them, they're not highly heat producing. And so you won't have these kinds of effects. You'll have all the geochemical retardation effects. And so if we look at the dehydration reactions, there's some volume effects. They're not so large. The important thing is that zeolites contain H2O molecules in them. And if you heat a zeolite, you can drive some of that so-called zeolitic water out of the structure. The amount of H2O in a zeolitic tuff is comparable to the amount of H2O in the pores. So it's really an important amount. You can't just ignore it and say, oh, it's in the mineral. It's not important. It's H2O just the same. The nice thing is, if you look at this thing and we heat it up, as we cool, the dehydration reactions are mostly reversible. So all the zeolites will say, give me the H2O. They will take it, they want to take the H2O back. So instead of the H2O being present as liquid water, it will be sucked up like a sponge in the zeolite. And something that's really nice that we, in my group, showed very clearly, you have to take advantage or have to consider the fact that H2O in zeolites is not this. And that's why I'm being careful not to say water. I don't talk about water in minerals, because this is water. By definition, this is water. It's hydrogen-bonded H2O molecule. The H2O in minerals is not this. So don't call it this. Call it H2O. And it's important because they're different things. The properties of this are determined by hydrogen bonding between H2O molecules. So the viscosity, the boiling point, the freezing point, that's all due to hydrogen bonding. In most minerals that contain H2O, those H2O molecules aren't talking to other H2O molecules, they're talking to the structure, and the calcium, and the oxygens, and the aluminums. And so it's really different. So that's why I said 100 degrees C is not magic. It's magic for that stuff, but not with that. And so all of these reactions depend on the humidity. If you brought a zeolite into this room, it would probably contain a little bit more H2O in the structure than if you took it outside, because it's getting pretty humid in here. So this is the structure of clinotulite. If you don't know about clinotulite, you should know about it. It's the most common zeolite on Earth, on the surface of the Earth. And it's got this aluminosilicate framework with these large sites containing H2O molecules and these exchangeable cations that want to swap with cesium and strontium, for example. And I did a lot of X-ray diffraction measurements, and these are for 4 different samples: the sodium, potassium, and calcium exchange clinotulite, and the natural one, where I heated the sample. That's the initial one in room temperature. I evacuated it, and then I heated it, and then I put it back in the room. And the red ones are in vacuum during heating, and you can see a pretty big volume decrease, 8.4%. The blue ones are heating in room air, and so there's a lot of H2O molecules around, and so you always have an equilibrium between the H2O in the structure and outside, and they don't dehydrate nearly as much. And so the natural one here, dehydrated at 250, it lost about 2% of its volume. So the volume effect is measurable, but not so large. You might wonder, is it important? We wondered the same thing. And we did some very nice rock mechanics experiment on pieces of core. So we took cylindrical pieces of core. In this case, this is the devitrified welded tuff that's largely feldspar and silica minerals. We took the zeolitized Calico Hills tuff, which is like Neapolitan yellow tuff. It's a nice solid rock. We had a core of that. We vacuum dried these cores, so we didn't heat them at all, just put them under a roughing pump vacuum. And so they dried somewhat. But remember, it's not this, and so a lot of H2O remained in this, but much of it came out. And then we put these in a steel jacket and we put strain gauges on the outside to measure what's happening to this, and we immersed these things in water. Just liquid water at room temperature, and we measured. And so you have a zeolitic tuff that when you evacuated it kind of shrank, and it's held now in a steel jacket. You put in water and it's expanding. It's trying to expand. And you can measure that with the strain gauges. And so here's the stress generated. Tokopah Spring tuff, probably it's due to very small amounts of clay. So we had about 1 megapascal stress. Very quickly equilibrated. This, the zeolitic tuff, continued to hydrate as the H2O molecules made their way into the structure expanded, the volume increased, and we had about a 10 times larger stress generated. And so that tells us a couple of things. This slow thing tells us that the rock is fairly impermeable, but it tells us that these volume effects are going to be very important for rock strength. So if you heat the rock, you'll have the inverse of that, and you'll have tensional stresses and crack the rock. So, for all of this is very nice science, and it's also very important in real life. We can also measure the energetics of that H2O, not this, in the zeolites. And we do that by measuring the amount of H2O that the zeolite takes up as a function of the atmosphere around it. And so that would be 0% relative humidity, and this would be 100% relative humidity. And this was all, the humidity was established at room temperature. And this is a fractional water content of 1 is the most you can get in. And so you can see that as you increase temperature, you get less and less into the zeolite. If we analyze these data using some standard geochemical methods, we can extract what we call the enthalpy of hydration. And these are the partial molar enthalpies. This is the enthalpy of condensation of H2O, or vaporization if you change the sign. So it's about 40, 41. And look at the H2O, the enthalpy of essentially removing the H2O molecules from the zeolite. This right there tells you that the H2O in zeolites is not this. If it were this, it would just pop right out, no problem, takes very little energy. But you can see as you remove H2O molecules, we can use calcium as an example. As you remove H2O molecules from the zeolite, the remaining H2O molecules are holding on more tightly. They're interacting more strongly with the structure. And so it takes more energy until the point the last few H2O molecules in clinotillite are just hanging on for dear life, have an enthalpy of hydration 3 times that of liquid water. Again, okay, this is nice science. Is it important? Yes, it's important. Because when we do all of these very sophisticated computer models talking about what is the temperature of Yucca Mountain going to do as it heats, if you ignore that enthalpic effect, you'll get a very different answer than if you include it. Because when you heat Yucca Mountain, the zeolites are reacting. And this is an example of a very simple calculation we did. It's just a small block, and it's probably the most conservative example of potassium clinotillite. And if we say clinotillite, we're going to ignore clinotillite. So as you heat the rock and nothing's happening, you get to a temperature of almost 400 Celsius at 800 days. If you allow clinotillite to dehydrate and you consider the enthalpy of dehydration, you see a break due to pore water, and now you're putting energy in, you're putting heat in. If you think about heat, like you can have a teaspoonful of heat, like you can have a teaspoonful of sugar. It's a thing you can add, and depending on your material, your temperature will change. And so we put heat in, and it takes a lot more heat. The zeolite is saying, I need a lot more energy to remove my H2O than here. And so it buffers that temperature. So instead of 400, we went to 250. So those kinds of effects are very important. So the enthalpic effects tell you, again, the water and minerals is not this. The H2O in minerals is not that. So one final example, very nice geological thing. You're going to create a long-term, basically low temperature metamorphic event in the mountain. Temperature is pretty low. If you're a metamorphic petrologist and I tell you that I would like to study mineral reactions at 100 C, you'll go away and go to sleep and have a beer or something. Nothing, you don't study those, but sedimentologists and clay mineralogists study that because a lot of very interesting things happen at low temperature. And so this is where we were able to use the natural rocks at Yucca Mountain to tell us what has happened. And so we already see these. If we go deeper in Yucca Mountain, we see that clinotidolite eventually with depth disappears and reacts to analcime. Mortonite reacts to analcime, and smectite, just like it does in piles of sediment, eventually reacts to illite. And so we were able to interpret the temperatures at which these happen, primarily using geothermometers. I'll show you my favorite one. And we also used a lot of fluid inclusions. Because remember, again, there's a large volcanic caldera just north of Yucca Mountain, 2 kilometers north, that heated the whole mountain. So there was a very large thermal profile. So I used the illite smectite geothermometer, and there are a lot of data, but the geothermometer works by you interpret X-ray diffraction data and figure out where you are on this scale, and you can extract essentially to what temperature has my rock been exposed. So the illite smectite geothermometer is quite useful in fairly low temperatures. So you can see we're down below 140 C. So it's a very useful thing. Metamorphic petrologists don't even worry about this mostly. I used this, and fortunately I had evidence in a number of the deep drill holes of this sort, and I was able to determine the paleo-geothermal gradient and interpret the temperatures. You might say, who cares? Well, number one, you care because if you react clinotidolite to analcime, you've destroyed a mineral that's quite important in retarding the migration of cationic radionuclides. And this is one of the reactions you can write. And you can write a lot of other ones. There are a lot of other ones in the literature that are incorrect. It's really dependent on the activity of silica and temperature. And what we saw in the rocks was that as clinotidolite disappeared, we formed analcime. It's a sodium zeolite. Most of the clinotidolite at Yucca Mountain contains calcium and sodium. We also find calcite. The minute analcime appears, we find calcite. That's where the calcium from the clinotidolite went. And we find no opal CT and a lot of silica. And so you can get a large volume change going from here to here. If this precipitates as quartz, your delta V is 22% negative. If it precipitates as cristobalite, which it won't, 17. If this is aqueous silica and it leaves the system, you have a minus 50% delta V. So very large decrease. So if your repository causes that reaction to occur, you'll have pretty large, maybe catastrophic volume decreases in that zeolitic horizon. So it's very important to understand that. And so when I used the illite smectite geothermometer, these are the temperatures based on the rocks at Yucca Mountain. So this is tailor-made to Yucca Mountain. We find that the maximum temperatures in which clinotillite was stable at Yucca Mountain were 90 to 100 C. Morganite, slightly deeper, so slightly higher temperatures. And the analcime actually, in the deepest drill holes, analcime transforms to albite. And so it's much more stable. So really quite a fun example of using mineralogy and geochemistry to get some very important bits of information. So, okay, I'm almost done. See you squirming around. I'd be sleeping by now. I don't know how Italian students do it, but they asked me to give lectures in Ferrara. I had to give 6, and they said 2 hours, please. And people stayed awake. In the United States, everyone would be sleeping, including me. But just to bring everything together for you, mineralogy is, as you saw, it's really important to retardation, but you just have to always consider the source of the waste and the fact that we're so far beyond the idea that minerals are important to take cesium and strontium. There's so many more complex things. And keep in mind that you may be putting waste in the Neapolitan yellow tuff. You want to pay attention to your transport pathways because they may be in fractures that may contain something completely different. So you always have to worry about trace phases. And in fact, we saw evidence that if you ground up a piece of Yucca Mountain tuff and tried to find manganese oxides, you wouldn't find them. They're present at probably the 0.05% level. But you saw that they controlled cerium migration and likely the actinide migration. So trace phases are really important. Thermal reactions, they're important for spent fuel, for any heat-producing things. The kinds of things that you have in Italy, this is not so important, but you saw that they affected mechanical properties from those strain experiments we did. Thus, they're going to affect the hydrologic properties because if you crack the rock, you make new pathways. And those pathways don't have manganese oxides in them. They're brand new pathways. You might destroy some good things, but overall for Yucca Mountain, the mineral reactions are what constrained the maximum amount of waste we could put. If we didn't have to worry about the temperatures, we could put a lot more waste into Yucca Mountain. So that, I'm proud to say that mineral reactions constrained the waste loading. So minerals had an important effect. And then what I just showed you, you can really get some quite nice fundamental geological information on the past history, and that's the key to, for example, these temperatures at which things might alter. So use your geologic knowledge to take apart the rocks and say, what happened in the past? So now the past is the key to the future. And so just remember, geologic repository implicitly assumes that you're going to look at everything. Don't go into it as a mineralogist and forget the hydrology or the rock mechanics things. You want to understand it all. And I think talked enough about that. You don't have to worry about that in Italy. Spent fuel, you do have to worry about that. And if you're working in France, or if you go to work in France on their repository, I wouldn't be surprised if some of you, or one or more of you, go to another country in Europe because there are repository programs in other countries that are using nuclear power. So it's a good place to work, an exciting place to work, and you can get tremendous amounts of satisfaction from using your geological background to solve a really important applied problem. Thank you for staying awake.
Thank you, Dave, for your interesting lesson. Please let the last 2 points.
Okay.
Because sono molto contento che lui abbia messo in buona lista questi 2 punti. Bisogna comprendere quelli che sono tutti gli aspetti geologici, quindi non sarà solo il mineralogista, non sarà solo il geologo, ma bisogna interagire, soprattutto poi da mineralogista, l'importanza della mineralogia che può diciamo, far capire quali sono diciamo, le reazioni per il trasporto e che possono avvenire in luoghi che dovrebbero essere sicuri per definizione, ossia quelli che devono ospitare i rifiuti di questo tipo. Ma il secondo punto credo che sia veramente la cosa più interessante. Ok, ci sono domande? Qualche richiesta di chiarimento? Petrografi, chimici? Ma anche le domande.
Are there zeolites on Mars?
Are there zeolites on Mars? That's an interesting question. We do not have good evidence for zeolites on Mars. I have some X-ray diffraction data from Mars, and we've seen no evidence for zeolites. But of course, we have 20 X-ray diffraction analyses, and you can imagine saying, what's the geology of Earth based on 20 X-ray diffraction? Who knows? There are some, we have global spectral data, essentially infrared spectra, near-infrared spectra, for the whole planet from orbiting spectrometers. And some people have said, I think I see zeolites, and I would love to have this. I'm not convinced, and unfortunately, zeolites are not so easy to see spectrally. They look a lot like, the framework part looks a lot like feldspars. The way you can determine the difference is the presence of H2O, but a lot of things, there's H2O all over the surface of Mars. And so I would have to say at present, although altered basaltic terrain, you would expect to find perhaps cabezite. You don't have any evidence. Too bad. So can't put your waste on Mars.
Are there other important zeolites to play with these things? You mostly rely on Plino-Tyler. Other types of zeolite other than analcime and mordenite. Yes.
Yes. So, are there other types of zeolites? If you mean at Yucca Mountain, the only zeolites we saw in significant amounts were clinoteolite and mordenite. We saw in fractures some other kinds of zeolites, stellarite. In general, most of the zeolites behave similarly with respect to radionuclide sorption. And so maybe they're a little bit more efficient for cesium versus strontium, but in general they behave very similarly. But at Yucca Mountain, clinoteolite is by far the dominant. Mordenite, lesser, analcime, if you want to call it a zeolite, is very deep. It's only in rocks that have experienced higher temperatures. And so, but yeah, only those 2 or 3.
So, this the Neapolitan yellow tuff could not be very an excellent repository for, in general, apart from fractures and
Apart from population,
apart from other geological problems. Neapolitan yellow tuff, the Campanian bright, and so on. Our tuffs.
Well, it's in places it's quite zeolitized, right?
yeah.
Yeah.
And plus they are selected for cesium and strontium, but you said that cesium and strontium don't exist.
Yeah. It depends on the waste. The material that I've seen personally, I think, could be quite good. As good as the zeolitic horizon at Yucca Mountain. For example, for the types of radioactive waste that Italy has, it could be quite good for some that have cationic species. And so if you have cesium is in medical waste, it's quite good for that, and their flow through the Neapolitan yellow tuff, I believe, would be predominantly matrix flow. The advantage,
Not fracture. Not fracture.
yeah, the advantage of matrix flow is it's easier to predict.
Simulate.
Yeah, to simulate by a computer. If you have to predict fracture flow, you can make a story and nobody can tell you. It's like telling what's on,
You can simply use limestones.
yeah. But no, so I think it could be good, but again, you have to worry about the other aspects. You have to worry about the water table, and you would not want to emplace. Ideally, you don't want to emplace a waste repository in the saturated zone. Unfortunately, most of the European countries north of you are considering that because they don't have deep unsaturated zones. So the water is the thing that will carry most of the waste.
How do other countries producing nuclear waste figuring out to manage this kind of problem?
France has a large program. Sweden has a large program, and their programs in general rely on some geological barriers, and they rely on rocks that have higher concentrations of smectite.
They don't have any zeolite.
Right, no zeolitic rocks. Some salt, but the idea in that case is you have a geological system, but they're really focusing, because of their restrictions, they're focusing almost solely on the hydrologic aspect, the water aspect. And if you have rocks that are high in smectite, you can have very low permeabilities. So you have, like that example, you have water can flow, maybe not interact so much with the rocks, but the permeability is so low that the flow rates in the end are not very fast.
More mechanical aspect.
Exactly, yeah, more hydrological, mechanical.
I have maybe a more philosophical question. Do you think that all of these studies that you and your colleagues made on the Yucca Mountain help, I don't say people, but the politician to have a more wise decision on these kind of stuff? Do you think that it was worthy the $9 billion spending to increase the sensibility of people, of politicians to reach the goal of treating waste?
Well, I'll say before I answer directly that question, I can think of one area that benefited tremendously, and that is unsaturated zone flow and transport. It caused an explosion of that field. Before Yucca Mountain, maybe there were 1 or 2 people in the world studying. And now it's a bona fide, it's a real area of study in hydrology, and it's an active area because of things like this. And keep in mind, there are many kinds of waste that we all have to deal with that aren't radioactive waste. So you have landfills. If you have a landfill where you throw your trash, you know there's some not so good stuff in there, and you want to make sure you want to do studies on that. So that, I think that's one of the huge benefits of that $9 billion. Do I think it will influence, affect
The
politicians? I think I can categorically say no. The politicians, I mean, look at how many politicians in the United States, faced with overwhelming results from research on thousands of scientists about global climate change. We have many, many politicians who say, I don't believe it.
Not based on scientific.
No, it's based on,
They're fucking.
yeah. So no, unfortunately, and I think that's the case probably everywhere in the world, that we can, so that's our problem. We have to communicate effectively. And there are very few scientists who can communicate effectively to politicians because it's very difficult to communicate. As you know, if you go home and to Nonna And oh, what are you doing? Oh, I love you. So nice to see you. What are you doing? Oh, I'm working on mineralogy.
Okay.
You have to communicate to people like your mother and your grandmother effectively in a way. This, you will be a famous person. I'm completely serious. That you will be a very valuable citizen and a very famous person because the politicians will want to hear what you have to say. So you communicate in a way that your mother and your grandmother can understand. Show them why is it important to do this. You'll be rich and famous, or at least famous.
Qualche altra domanda? Curiosità? Ok, so, grazie di nuovo per essere qui.